Today is a somewhat exciting day because we are going to begin our initial discussion of the last big topic that we have left to cover in this course. Maybe a few other little topics sprinkled in at the end, but there's a big main chunk that we have left to cover, and we're starting it today. And that chunk is studying cycle devices. So almost everything that we've done in this class previously, studying all the different properties in depth, studying the laws that relate those properties, and studying the laws of thermodynamics that govern how entropy can be generated and change, and also studying conservation of energy and different forms of work, all come together in this study of different devices we can have that operate in cycles to do things that we want. And so I want to refresh your memory of two main cycle devices that we've talked about, or really one device that always operates like this. It's got up here, a temperature that's hot, and down here, a temperature that's cold. And the device operates by bringing in some heat from the hot reservoir and bringing out some heat into the cold reservoir. So it's operating between two temperatures. And we saw in the second law of thermodynamics why that's necessary. Okay? We have to have two different temperatures for any machine like this to work. And then that extra, what it's actually trying to do, is trying to generate work, okay? So we're always gonna leak a little bit of heat out into the cold reservoir, but we wanna convert as much as possible into work. And we called this a heat to work machine. That was just my title for it. However, we've also discussed the second type of machine, which is that we can take this and we can run it the other way, okay? So we can, let me draw this picture again, go from a hot reservoir to a cold reservoir, but this time run everything in reverse. So instead of heat spontaneously flowing, because the heat wants to go this way, hot to cold, it'll do that naturally. And we use that natural flow to pull work out. We can put work in exchange for reversing that natural flow. Temperature cold going out. Q, I'm going to call this QH for Q low. Okay, so there's a high and a low. So there's a heat amount coming from the low temperature, and there's a heat amount going to the high temperature. So we can, in a certain sense, reverse the pipeline and make it flow from cold to hot, as long as we're willing to have some work that goes into the system, okay? And this we had called a work to heat machine. Now, these were just my colloquial titles that I think make a lot of sense, but I want to tell you what the actual titles are in case you see them come up. So this is called a device operating in a cycle, right? Both of these black boxes here, that I call them black boxes because right now they're unknowns. We haven't even broached the topic of what's happening in there. And so both of them I forgot my train of thought, but they're both operating in cycles, okay? Both of these are operating in a cycle. And so this one, the heat to work machine, we call a power cycle device, and this we call a heat pump cycle. These names make sense because if work is what's coming out of this, usually we are interested in how fast we can do it. So we're really interested in work per unit time, which is power. So that's what we want. it's named after the thing we want out, which is power generation, or work pulled out. This one is named after the thing we want, which is simply just to reverse the flow here. We want to pump heat in the way that it doesn't naturally go. We're willing to put in work to create a heat pump that pulls it against its natural flow. So power cycle and heat pump cycle are the names of these two different categories of devices. And you'll remember that I just want to review something. For this power cycle, we had an efficiency, eta, which was equal to the energy output over the energy input. And I've derived this about 3 times on the board for you. So just look back through previous videos and you'll find this. But that comes down to 1 minus Q low over Q high. Okay? That's the efficiency of that. And we know that the work from this, let me circle this to refresh your memory. We know from the first law of thermodynamics here that the work is Q high minus Q low. Okay? The other thing we know about eta is that eta is always less than or equal to 1. So let me also circle this. These are both important points. So efficiency is a word that we hear every day, and even without my formal teaching that you can go back and see, even before you stepped into this class, I'm sure that you had some sense of the word efficiency. Now, the reason that I harp on this efficiency and I circle the formulas is because actually with this guy right here, this heat pump cycle, or the work to heat machine, it's going to be a slightly different story. Because this has an efficiency and it can be calculated in the exact same way. And we'll do homework problems in a lab where we do calculate the efficiency of this guy. But the thing is, the efficiency is not what we care about. Okay? And you'll see what I mean by that in just a second. Because let's talk about what we care about doing. So with a heat pump or a work to heat machine, we care about pulling heat from one space, which is the cold space, into another space, which is the hot space. That definition, it makes sense, but it leaves open a question. What are we actually trying to do? And that question, what it'll do is it'll divide this picture into 2. Okay? The first thing that we may care about, let me draw this sketch real quick. This is QH coming out, QL going in. And this is work coming in. All right, so I've just drawn this sketch really crudely twice here. The first thing that we may care about, or be actually trying to do, is pull as much heat out of a cold place as possible. So when we're trying to look at like what's the efficiency, or you'll see it's actually not efficiency, it's something different, but we're asking how well does the machine work? We want to compare them. Okay, I built one, you built one, how do they perform? We have to look at what we're actually trying to do. And if what we're trying to do is pull heat out of a cold place, then we're looking at this portion of it. So this is a magnifying glass, okay? Because the part that we're trying to study is how much heat are we pulling away. Remember down here there's a cold reservoir? We are pumping heat out, that's true. And energy is conserved. So whatever heat we're pulling in plus the work that we're putting in is still, you add those together and you still get the heat going out. Nothing's changed about that. There's no conservation of energy problem. It's just that we don't care about this part. We don't care about the heat going out. What we care about is how much heat we're pulling actually into the machine, away from the cold place. And that, the name of that, is I'm misspelling words left and right. Refrigerator. Refrigerator has a D in it, but fridge does not. Okay. So this is, that doesn't look right. How did I write it on here? I'm gonna stay with the D, but that might be right. That might be wrong. Anyway, moving on. That's the name of this. As you can suspect, we are going to contrast that with if we're studying this, which is in this scenario, right? We are pulling in heat to our machine, but we don't really care how much heat we're pulling in. We're not interested in that because it's not what we're trying to do. What we're trying to do is we're trying to pump as much heat out of our machine as possible because we're trying to heat a space, okay? So the thing we're studying, which is why the magnifying glass is there, we're focused on the amount of heat that we can pull out. So this is something that people get confused by, thinking that there's some huge difference between a refrigerator and then down here the word for it is a heat pump. Okay? There's not. They are the same machine. I want you to understand that. This machine and this machine are the same. Okay? The only difference between them is where our focus is. Are we focused on how much heat we can pump out or how much heat we can suck in to our machine? Away from the cold area or into the hot area. And because we're concerned with this and not the work, over here we were concerned with getting out work, and so the thing we were focused on was efficiency. Over here, the thing that we want to focus on is not efficiency. It's something called the coefficient of performance, okay? Coefficient of performance. And first I'm going to do the coefficient of performance for the refrigerator. So I'm going to put a little R there. COP, or coefficient of performance. That's what I mean by that. And as before with the efficiency, we looked at the energy out over the energy in. Okay? I'm going to write the same thing at the detriment of some confusion, because this is an easy way to remember how to write these formulas. The book does a very similar thing. They don't use the exact terminology, but they also invoke the same confusion. What I mean by E out and E in are not the same as I mean by E out and E in if I was looking at a power cycle. The way in which they're the same is that let me look at the E out and E in that I'm focused on, okay? So the energy output is actually how much energy can I suck out of the cold space, right? That's my energy output. What am I focused on? What can I suck away? So that is actually QL. And then the energy in to the machine is the work. Now we know that for both of these machines, we still have this equation that holds true. Work is the QH minus the QL. So I can write this as QL over QH minus QL. And then this thing simplifies, and when I say simplifies, this is a fine form to leave it in if you want, because the form I'm going to simplify it to may look more confusing to you, but what I want is I don't want this duplicate number. Like if QL was 5, I don't want to have to plug it in there and there. I just want a formula that I can plug it into once. So the way I do that is by multiplying the top and the bottom by 1 over QL. So that on top, I get 1, and on the bottom, I get QH over QL minus 1. So this is perfectly equivalent to that. It's just this is simplified because it only uses each number once that you have to plug into, okay? So I am going to circle this, and I'll actually write down here again that this is COP for a refrigerator. Now, Actually, before we keep discussing this, why don't we do this one real quick? So for this one, it's the same thing, same calculation. COP, this time I'm going to do HP, COP for a heat pump. This one is, again, going to start with E out over E in. Only this time, again, I'm changing what I mean by E out. It's the thing I want to focus on, which is the Q hot, the heat that I can pump out into the hot space. So this one is Q hot over work, which is equal to Q hot over Q hot minus Q low, Q high minus Q low, which happens to equal, if I multiply top and bottom by 1 over QH to do the same trick, 1 minus QL over QH. And one more time I'll write this, was the coefficient of performance of a heat pump. So, it's the same machine. Again, do not get confused that this is a different machine between a refrigerator and a heat pump. They're the same thing. Think about it like this. Your fridge at home that's cooling the inside of the fridge, if you go stand behind it, put your hand down there, it'll be very hot because it's pumping heat out. So your fridge is designed to cool a cool space, but it's the exact same machine as you would use if you were trying to warm up a warm space. So your fridge is always actually warming your kitchen because it's pumping heat. So these aren't two machines, it's one machine, and these are two different perspectives. And the reason that the coefficients of performance are different is because they're just two different perspectives on the same machine. And so if they're the same machine, we would expect them to be linked, and they are. It actually turns out that, I'll write this here, the coefficient of performance of a heat pump equals the coefficient of performance of the refrigerator plus 1, okay? And this is not black magic. If you just trace through those equations and find out, it's actually really not hard to do. Replace this work with this, and replace this with the work minus the other one. And you can rearrange and shuffle and say that these two equations that are circled in blue fulfill this, okay? So they're very closely related. They're almost the same thing, only they differ by a factor of 1. So let's look at the coefficient of performance of the heat pump. What you'll notice is look at what is here in the bottom. 1 minus Q low over Q high. Q low over Q high. This is the efficiency eta, okay, of that machine, of the power cycle machine or the heat to work machine. And so what this means is that this is 1 over eta. Okay, I'll stand here so you can see them both. So think about that for a second. This still has an efficiency. This machine has an efficiency, and the efficiency is the same as if it was this machine. It's just that over here, what we're thinking about, what we're trying to get out, is the efficiency of work that's coming out. And over here, we're putting work in. So we're not concerned with the efficiency of the machine. What we're concerned with is 1 over the efficiency, or the opposite of efficiency. So think through this one level deeper again. If we know that efficiency has to be less than or equal to 1, it can be anywhere from 0 to 1, but a perfect machine is 1. So it's capped at that. It's a theoretical maximum. Then that means that this coefficient of performance has to be greater than or equal to 1. So 1 is a theoretical minimum. It can't go below 1. It's going to be 1 and above. It can be 1, 2, 3, 4, 5, 6. It can be 10. It can be 100 in principle. Okay. What is the limit? The upper bound? How high can it get? Well, if eta can get down to 0, then we'll do our, don't tell the math department people, shh, but we'll do our divide by 0 trick. If the worst eta can get is 0, then 1 over 0 is infinity. which is the best that the coefficient of performance can get. So there's nothing stopping this from going all the way up to an infinite coefficient of performance. Okay? What that would mean is that we have this heat flowing for free and there's no work. The second law of thermodynamics says it's not actually free. We have to put in some work. But the second law of thermodynamics doesn't give a number, like it has to be a maximum of 200 joules or something. So it just means we need a little bit. And the better and better machine that we can make, the less and less work we have to put in to drive that heat in that direction. So as we get the work smaller and smaller and smaller, heading towards zero, never getting to zero, but heading there, the coefficient of performance is heading toward infinity, never getting to infinity, but getting larger and larger and larger. So the coefficient of performance really just has to do with how good can we make our machine, okay? Over here, because that's a slightly different formula, this turns out to be equal to 1 over eta minus 1. You can check it from the formula here by plugging in the equivalency of eta, or you can look at this relationship. That if we have this, we'll just move to 1 to the other side, okay? And this one just happens to be greater than or equal to 0. So for a refrigerator, we can have a coefficient of performance of less than 1. We can have one that's like a half or 3/4 or something like that, but it still can't be negative. And in most cases, it really is still greater than 1, okay? So this can also go up to infinity, okay? Because if I have 1 over 0, infinity, yes, I'm subtracting 1, but infinity minus 1 is still infinity. In other words, the minus 1 goes away real quick. Just look at it as numbers spiking up. So now we're not at infinity yet, but we're at 1,000 with this number, let's say. Eta is 0.001. It's a really bad efficiency. So we're at 1,000 minus 1, that hardly makes any difference. And as we get higher, if this was 1,000,000 minus 1, it makes even less difference. So by the time you get all the way to infinity, subtracting 1 makes no difference. So that number can also get as high as we want. The last point to make on this is that the efficiency and the coefficient of performance, these two things, they are, in a very real sense, inverses of each other. This one's a perfect inverse, but also in the sense that if you think about it, the worse the coefficient of performance is, the better the efficiency is. But the worse the efficiency is, the better the coefficient of performance is. Now that makes sense. And it makes sense because these are the same machine, but they are the opposite of that machine, right? This machine is doing a completely different thing than this machine is doing. Just look at these two pictures. One wants to get work out, okay? Work out. This one wants to put work in. And so the better that this machine is at getting work out of it, the worse this machine is going to be at doing its thing, which is putting work in and doing its thing, and vice versa. So an AC unit makes a terrible work output machine or power cycle machine, but a car that we're trying to get work out of, a car engine, makes a terrible AC unit, okay? So they're inverses of each other, and they have to be built for a specific function. Okay. Do I have everything covered here? So here's what we're going to do. We're going to take a look at what's inside this box. We are going to, as I lift this, finally zoom in, okay? Now I've got some stuff I've already written up here to save time, but what I mean by zoom in is now we're going to think about building real cycles. And the way we're going to keep track of those cycles is by plotting points on our phase diagram. That's why we introduced this. We've got a PV diagram, we've got a TS diagram. And so at one point, let's say we're here, and that'll correspond with the point over here. And then let's say we throw in another point that we go to up here, and maybe that one goes to this point. And then maybe we have a third point. And then we can complete a cycle. Okay? We've gone around in a cycle. And this one also, we've gone around in a cycle. That's a cycle of 3 points, and it's the minimum for a cycle. If we had 2 points, we wouldn't be able to make a loop or a cycle. Okay, so we need at least 3. But we can have 4. Let's say we put a point up here that corresponds to a point up here. So now that's our cycle. In some cases, we could have 5. Okay, go out to this point and back. Okay, so every time we put a point on one of these plots, we'll have to find where the point on the other plot goes, and we'll connect them up with lines corresponding with the cycle. Now, here's the difference between those two machines we were just talking about. The one that is a heat to work pump and the one that's a work to heat pump. Whether we want work out or whether we want work in. The cycle goes in the opposite direction for each one of them. So let's say that this was the direction, you could draw it on all of them. This was the direction of the heat to work pump. Then in order to get the other machine, all I would do is take the same cycle, but design the machine to run the cycle backwards. And when I say redesign the machine, I really do mean different components usually. It takes a different physical thing to make the pressure increase or the pressure decrease, right? Whichever direction I'm going on this. So right here, right, I'm spiking the pressure up. If I'm going this way along this theoretical process, I'm going to use, let's say, a piston to increase the pressure. And that will create, let's say, a heat-to-work machine that gets out work. To create the other one, the one where I put work in and get heat flow back, I go the other way. So this time in this cycle, I'm going to decrease the pressure right here because I'm going to go backwards. And that's going to require an actual different component. So real quick, here are some components that we can use in, and these are just some. These are the ones that I could literally think of off the top of my head. If you Google a list, you're going to get a better list. But here are some real world things that we're going to use to build these cycles. So compressors, which are pumps, pistons, an injector, which is adding a little bit of mass that can often make an explosion. When we study Otto cycles and diesel cycles, we'll study injectors. Nozzles, those just take a wider flow and compress it down, right? So when there's a flow, we can just change the pressure, or we can open up a narrow flow to a wide one. A turbine, kind of like a nozzle, but the pressure in the system is used to turn something and get work out. Heat exchanger means that we can have maybe 2 fluids where one of them is giving off heat, and in the special case where that fluid, the other fluid is maybe the air, so there's just something like hot water and it's giving off heat to the air, we could have a condenser, or if the air is giving heat to the water going the other way, we could have an evaporator. And then maybe resistor, that's a way to put electrical power into heat in the circuit, like the way a toaster works. So, and on and on. These are just some real world components that we can start to look at. How do we build these cycles? So, there's 2 points on this graph that I want to look at, which are that the work from any cycle is the area enclosed by the cycle. So to prove this, it takes calculus, and in most cases to do this, to even calculate it this way, it takes calculus, but I just want you to realize this and know it as a fact. This area in here, that is the amount of work in that cycle. Now, is it work in or work out? It depends on which way the cycle's going. If it goes this way, then it's work coming out. If it goes this way, then it's the work that we have to put in to run. But that's a nice handy trick, and it's a beautiful picture thing, that this area inside here is the work. The second point we have to bring up is that from each one of these points to the next, there are like perfect processes. Okay, we'll talk about that in a second. But these perfect processes are theoretical. Okay, so the cycle diagram for any cycle is theoretical. Real cycles are smooth. So what I mean by that is that where this imaginary cycle goes and makes this shape from one side to the other, and it's got these sharp corners, in the real world, if you were to go in the lab and measure it, the cycle may go more like that. Okay? It would smooth off the corners, and over here it may look something like this. Okay, it'll follow the basic shape, but it won't be those perfect points, because in the real world it's going to be a smooth cycle. So as we draw these perfect pictures, we're making theoretical calculations of these things. We can't calculate something like that that's all roundy and stuff, but we can calculate the straight line ones. So going back to these straight lines, these are obviously process paths, and there are different types of process paths that we can have. Okay? If I have an isothermal process path, that means I have no change in temperature. Some of these we've gone over. Isobaric, constant pressure. Isochoric, no change of volume. Polytropic, we won't see that a lot. I threw it on the list because I want you to know the term. And this has a weird condition. Pressure times volume to any power is a constant. Okay, that special name, it's used. It's a thing that people use, polytropic. Then isenthalpic, we talked about enthalpy last time. This means that the enthalpy is not changing. Then we have adiabatic, that no heat change. We have isentropic, no entropy change. This is the net entropy. And then we have reversible, which means that the generated portion, or the imperfections, that actually is zero. And so like last time we had those 3 stars. Basically this is our 1 star, this is our 2 star, and this is our 3 star. Okay, all these are really nice processes. Everything's smooth, everything's nice, it's flowing well. And basically this is like the ranking. This is the most perfect of the processes that we can have. But this is also a pretty good assumption that's like in a certain sense perfect. And same with this. So basically, in all of our study of these processes, what we're going to do is put different processes together, and it's like Build-A-Bear, okay? Only it's build a process. So what I mean is that I could say, well, let's see, I want to think of a process that first has isobaric, so a constant pressure, and it's going to expand, but stay at a constant pressure. And then I want it to be isochoric, so the pressure is going to change, but it's going to stay at a constant volume. And I'll build my process paths around the edge of my cycle based on choosing different ones of these like perfect building blocks for each leg of the cycle. And let me show you what some of the very basic ones are where people have done that. Okay? So this is like a PV diagram, and this is like a TS diagram, like those two we were just looking at. And these are 10 different cycles that we're going to touch on all of them. Some of them are going to have their own dedicated videos as we study each cycle. But I want you to get a feel of the variety. Every single one of these, if you compare, take them as a unit, PV and TS together, each one is different. Okay? So they're all different cycles, and they all have special properties of interest, and we're going to study these. So this is what I mean by like Build-A-Bear, like build a cycle. Take your side, whatever you want to be constant or special property, and build a cycle made out of that. And this is what's historically been done by all these physicists. The last note we have on this is that these names usually are the names of the power cycle, meaning the heat to work cycle, the one that gets work out. And if we reverse it to run it as like the refrigerator / heat pump, where work goes in and we get heat flow coming out, then we usually call it the reverse, whatever the name of it